Welcome to Einstein's Mechanics. In this episode, we are going to talk about method of separation of variables. This is one of the ways to solve a differential equation, a first order differential equation. So basically, there are so many ways to solve differential equations where we can use many other methods, but the first and simplest one among them is the method of separation of variables in solving first order differential equation. So anytime we have a first order differential equation such as dy dx 1 on y e function x equal to 0. This is a first order differential equation because we can see that the order of the differential equation is what? 1. Then also I can also have a differential equation which is in the form dy on dx is equal to 1 plus x. We have 1 plus y. This is also a first order differential equation. We can solve all these equations to get their solution. Let's also look at this. We can have a differential equation such as negative x dx is equal to, say, y dy. This is also a first order differential equation. And in an approach to solve these equations, we want to discuss the method of separation of variables. Now, this method, you have to understand it from the basis. So some of the functions of a differential equation, some functions of a differential equation can be separated into both x and y components. Just pay attention. Some of the functions can be separated into x and y components. For example, if I have a differential equation of x and y, I can separate them into a function of x multiplying maybe a constant and a function of what? Y. Are we good? So such equations where we can group the y terms and x terms can be solved by this method of what? Separation approach. Are we okay? For example, if I have an expression such as an e function x plus y. Remember, this can be separated into a of x multiplying e of y. Are we good? So this can be separated. Then again, if I have an expression such as xy plus x plus 2y plus 2. Remember, this function can be separated into this where we are going to get our x plus 2 and multiplying our y plus 1. So in this term, we are able to group the x on one side and the y on the other side. This is an idea of method of separation of variables. So what variables are we talking about? Here we have x and y variables. So we have x standing alone, y standing alone. Here we have the x and the y alone. But some of the differential equations cannot be separated. In that way, the method of separation of variables will not work. Let's look at an expression such as the natural log of x plus 2y. We see that we cannot do a separation for these terms. Something like sine x squared plus y, we cannot do a separation. Are we okay? Something like xy squared plus x squared. We cannot do a separation, right? Okay, so this method can be used, and such equations that can be separated are also called separable equations. Please, you understand very soon. Separable equation. So If I give you an example where you are to solve the particular differential equation, you are supposed to group the terms such that you are going to get a g function of y on the other side of the equation and another function of x on the other side of the equation. Please pay attention to this. Always, if you want to solve a first order differential equation, and what I mean by first order is the order or the power of the highest degree or the highest derivative supposed to be 1. And in such separable method, always we group a function of y with respect to dy on one side of the equation, and we group a function of x with respect to the x on the other side of the equation. So let's see an example. We are to solve this particular problem. So you just see a differential equation and you have to solve dy on dx plus this function y squared plus 3x is equal to 0. So you are supposed to solve this differential equation. So the simplest method as I am teaching is the method of what? Separation of variables. So don't be scared. This is a very simple one. So you try to see if you can separate. It's more or less like grouping like terms, sending one like terms to the other side. So here I want to send all the y to one side of the equation and send all the x to the other side of the what? Equation. So this is my original equation, dy dx plus 1 on y e function y squared plus 3x is equal to 0. How do I group like terms? So I want to separate them. This is what I would do. So here I'll keep my dy dx here and send negative 1 on y e function y squared plus 3x. Now I'll bring my y here. Dy is equal to, what do I have? I'm left with these terms. Negative e y squared plus 3x. Then dx is going to be here. I'm not done grouping like terms. Why? Because I still have y expression at this side of the equation. So what do I do? But then I know that when I have y dy is equal to, this is the same thing as e function of y squared multiplying e function of what? 3x. Everything what? Dx. Is that true? Yes. So here I can divide through by what? Negative e y squared divided by negative e y squared, such that this will take care of that. So at the end of the day, I'm getting y on negative e y squared dy equal to e 3x dx. So now I have made a separation, because on this side there are only y components and on this side there are only x components. Are we good? Alright, so I'll now be left to solve the equation. But then this side I can also make it negative y e negative y squared. Then I'll negate this. Dy is equal to e 3x dx. So this is the final expression. This is not the solution, but it's rather the separation. So when you check on either side of the equation, if it is with respect to y, they are only y functions. If it is with respect to x, they are only x functions. Are we good? So what we need here is now to apply our integration and solve the equation. So I'll apply my integral here. Are we good? That's why in differential equation you should be good in calculus. So here this is like negative integral of y Here we have negative y what square dy, right? So we have our dy equal to a3x dx. How do we solve these functions? Now let's tackle the left hand side first. What do we do? Here we can solve this integration by method of what? Substitution. So I'm taking the left hand side of the equation to solve. So if I'm to solve for negative integral of y e negative y square dy, what I will do is that I will let my u be equal to y square. Now the u dy is going to be 2y, where my dy is going to be what? Du on 2y. So I'm going to replace this dy with what? U. Then this y square with what? U. So this is what I'm going to get. So at the end of the day, my negative y negative y square dy is going to be negative. I still have my ye. Remember, y square is now u, and du, this dy is going to be du on what? 2y. This will take care of this, giving me negative u with respect to what? U. This is now simple. Are you okay? We have this 2 also, so I'll bring it out as 1 on 2. This is going to be negative 1 on 2. If you integrate this, you are going to get itself again. Are we good? So it is going to be negative 1 multiplying itself, which is going to give us a positive half a negative u. So this is the integral from the left hand side. Now let's look at the right hand side, where we have integral of e3x dx. This is very simple. So we differentiate this, which is 1/3 of the same function, 3x. Remember, anytime you do integration, you can add plus c. So now we can equate from the left hand side. We are having half. Let's replace this u by its original parameter, which is going to be half e negative y square plus c. So that is going to be e negative y square plus c, call this c1, call this c2, equal to the right hand side, which is 1/3 of e3x plus c2. So we can group all the c's, 1/3 e3x, and call it what? C say not. Are we okay? So this is the solution to the differential equation that we were supposed to solve. So first we did the separation, then we moved to the integration. Are we okay? Alright, so let's also solve for this function. It's very simple. Are we okay? Now we are to solve example 2. Solve for the solution for this function dx dy is equal to xy on y squared plus 1, where y is not equal to 0. So we have to solve for this. So as always, I'll just look at the expression. If it is possible to do separation, can I separate them and use the method of separation? Then that will be simple. If yes, then my solution, this is my question, dy on dx is equal to xy on y squared plus 1. This is going to be, if I'm trying the separation, then this is going to be, all this y will be y squared plus 1 multiplying dy equal to xy multiplying dx. I still have y here. Divide by y, divide by y. So y squared plus 1, everything on y, is equal to x dx. So now the separation is done. Are we okay? We have all this function in terms of y, here in terms of what? X. Remember, this can be written as, I can divide both sides by the what? Y. So y squared on y plus 1 on y for the dy side and x dx, which is later going to give me y plus 1 on y equal to x dx. So this is the simplest form. So I'll apply my integration. Integral of y plus 1 on y equal to integral of x dx. So integration, if I'm to integrate y, that is going to give me what? 1 on 2 y squared. And if I'm to integrate 1 on y, that is going to be the natural log of what? Y. Plus a c equal to the integral of this is also going to give me x squared on what? 2, that's half of x squared. Are we okay? So here we can see that our final answer, let's call this C2, C1, is going to be y squared on 2 plus natural log of y equal to x squared on 2. We combine the two constants to call it maybe C0, and this will be our final solution. Are we okay? So this is the answer for solving this differential equation using method of separation of variables. Let's look at another one. Now, we should solve the differential equation. We have dy on dx is equal to 2x on y plus 1. These are very simple examples. So solution. Our function is dy on dx equal to 2x on y plus 1. Can I do separation? Yes. So here I'll let the y go and the x go. So that is going to be y plus 1 dy is equal to 2x dx. So now it is a perfect separable equation. Apply integration. So integrating y will give us y squared on 2. Integrating 1 will give us y plus a c1. That's the constant of integration. Integrating this will give us what? We are going to get the expression 2 and 3x squared plus 1 c2. Is that it? Yes, that's what we are getting. So if we multiply through the equation, then what are we going to get? Let's multiply through. So this is going to be 1 plus 1, that is going to be 2, right? This is going to be 2. So if we multiply through by 2, that means we are going to get y squared plus 2y plus 2c1 equal to 2x squared plus 2c2. Remember, all these are constants. So you can replace all of them by just a single constant, x squared plus a c naught. This is our solution. Are we okay? So let's find an example using the method of separation of variables. So this time we are to solve this differential equation. The differential equation using the method of separation of variables. In some questions, you'll be asked to use this method. The method will be mentioned, but in most of the examples too, you'll be left to find your own method. Alright, so this is our differential equation. Tan y dx equal to minus cot x dy equal to 0. So trig functions, very simple. Don't be scared. What we know is that tan y can be expressed in terms of what? Sine y on what? Cos y. Is that true? Yes. And the opposite of this is what? Also cot. So cot of x is also going to be cos x on sine x. So meaning we can put this into the equation. When we say tan y dx should be equal to cot x dy, then we are going to get our sine of y on cos of y dx equal to cos of x on sine of x dy. Is it separated? No, because here we are having sine of y in terms of dx, and we are having this in terms of what? Dy. So let's try to make the separation very well. So all the x should come for the dx and all the y should come for the dy. Are we okay? So let's swap them. So meaning if we are swapping them, then it is going to be sine x on cos x with the dx equal to, here too we are going to get the cos y on the sine y with the dy. Is it separated? Yes. So now that we have the separation, we can apply our integration. What do we do? So let's take the right hand side, this part, and solve. So integral of cos y on sine y dy. If we are solving this in calculus, anytime you have integral of a function, which is this, if we differentiate this, we are getting the top. There's, for example, if we have integral of, let me simplify it for you, where we have f prime of x and f of x. The answer is going to be ln of f of x. Very simple. Anytime you have an integral of a function such that the upper one is the derivative of the lower one, then it is the natural log. The answer is the natural log of what? The function. So if we differentiate sine y, yes, we are getting cos y. So meaning at the right hand side, the final answer is going to be ln of what? Sine y, as plus c. You can also use the method of substitution to solve. If you are not sure with this shortcut, you can use method of substitution where you let your y be equal to that and you solve. Are we okay? Now let's look at the left hand side. From the left hand side, we also have the integral of sine x on what? Cos x. Is that it? Yes. So when we multiply this through by -1. If I multiply through by -1 up and down, so -1 divided by -1, integral of sine x cos x. I still want to use the shortcut. That is going to be integral of negative sine x, still negative out. So I will have 1 on -1 here, cos x. Now look at this. If I differentiate cos x, you see I'm getting negative sine x on top, right? So that is going to give me ln of cos x, but I still have the negative sign here, so that is going to be negative plus c. So from one side I'm getting this, and from the other side I'm also getting this. The same way you can also use method of substitution to solve for this. So in general, the final answer is going to be ln of sine y should be equal to negative ln of what? Cos x plus c. Very simple. Ln of sine y equal to negative the ln of cos x plus c. This is our final answer. Thank you for watching the first episode in the method of separation of variables. Check the second episode for more complex example. See you in the next episode. Subscribe to the channel.